Okay, good evening, everyone. We start today's session. Professor Gopti is going to start the presentation. We are going to do several things, but first the presentation, and then we are going to try to wrap up with several issues. We have identified that student in Data 650 has not grasped yet. So, but first with the presentation. Gopati, you can start.
Okay, thanks, Elena. If anybody can hear me, just raise your hand. I will try to fix the audio. Okay, so today we are going to cover mostly Sparc concepts and how Sparc platform can be used for machine learning. Okay. I will start with a brief refresher on distributed computing, including MapReduce, which you are already familiar with. And then we will move on to the Sparc internals and look at RDDs and data frames, and then the specific APIs for machine learning that would include transformers, estimators, and pipelines. And we will end with an example for specifically gradient descent. And then, as Elena said, we can look at other issues, and if there is time, I can do a code walkthrough of the Titanic exercise. Okay, so so that you can get started with your project on the low birth weight regression. Okay, so so you all know quite a bit about MapReduce now, but since we want to cover the internals of Sparc, I want to start with this. Okay, on the left side, I hope everybody can see my cursor. So you know that there are lots of compute nodes, and each node has a little bit of disk storage, and HDFS is already across all these nodes. It's already been installed across all these nodes. So the input file is usually chunked up and stored as bits, and you know that there are 3 copies of each chunk distributed across the nodes. Okay. So the way MapReduce works is the mapper function is applied to the local data, which is loaded into memory first, and it generates outputs. Okay, and from the specifically where the outputs go and how they are organized are the major differences between MapReduce and Sparc. Okay, so you can have a mapper function. You can also have a partitioner and a combiner, and these work in a sequence. Okay, so let's look at how the mapper operates on each piece of or each chunk of the file. Okay, so the mapper goes, and the mapper function is applied to the data that is locally stored, and the outputs are emitted. Okay, so you know that the outputs are usually in a key value format. So what you see on the right-hand side is the memory buffer on that particular node. Okay, so consider the right-hand side as the illustration of what is going on in one of the nodes. Okay, so the mapper function is working across the data in that small piece of file. Okay, and it is emitting key value pairs. Okay, so you got K3V3, K1V1, etc. Okay, that is the memory buffer in the first node, and for illustration, we have shown 4 different nodes here. Okay, so you will have 4 versions of this memory buffer across the cluster. Okay. Now, the partitioner, if you are going to use a partitioner, okay, this is how it works. It takes the key values and does some kind of a hash math with it. So essentially what it does is one simple form of hashing is it takes the key value, divides it by a large hash number, and then generates the remainder. Okay, so when it does that, the total number of remainders, okay, it is going to be a modular operation. So the total number of unique remainders will be equal to the number of reducers. Okay, so in this example, I've assumed that there are two reducers. Okay, so it takes K3, for example. That could, K3 key 3 goes through this hash function and it gets an output number of 2. Okay, K1 gets a number of 1. K4 gets 2. Okay, K4 again gets 2. So the remainder is unique. Okay, so every time you apply the same key value to that hash function, it's going to generate the same remainder. So it is a deterministic function. Okay, and it will only generate the total number of remainders it generates is equal to the number of reducers. Okay, now all of this is happening within the memory buffer on one node. Okay, now if you use the partitioner, then you get these keys, and then it needs to separate out each output collection into separate files for each reducer. So that is what you see in the next stage. Okay, it has collected all the key values corresponding to the partition value of 2. Okay, so this chunk of data will eventually go to reducer number 2. Okay, and here you see the ones all being collected together. So this will go to reducer number 1. Okay, now where does all this go? That goes into the local disk. Okay, and you can read up a lot more on the details. It's impossible to cover all the details. This is just to give you enough information so you can go look for more information and get a thorough understanding of the internals. Okay, but for now, just understand that the first operation of the mapper produces outputs which are stored in a memory buffer in a cyclic manner. Okay, so it's usually the default value of a memory buffer is about 100 MB. Okay, and 80% of that is allotted to the task. Remaining 20% is kept free for other operations. Okay, for other daemons and other operations. So if the memory buffer, if 80% of the memory buffer fills up, then the partitioner function and the combiner work together and start spilling the data in the memory buffer into the disk. All right. So that is what you see here. First, the partitioner splits the data into 2 files because we are assuming that there are 2 reducers, and then the combiner acts on each file individually, and then you get the key value of 3 appears only once, so you get K3V3, but the key value of 4 appears twice, so you get K4, and the 2 values are combined together. Okay, so that way these files are now smaller in size. When you apply a combiner, it's almost like a compression operation. You get smaller files. Okay, so now let's think about how many of these files will be generated. Okay, you got, let's say you got 1,000 mappers, okay, and 500 reducers. Okay, there are going to be 500,000 small files spread across the cluster. Okay. Now, each node will have 500 of these partitioned and combined files. Each of the 500 files has to get to the reducer. Okay. And this is going to happen across the network. Okay. So these are all the main operations that take a lot of time in MapReduce. Okay. So the first thing that consumes a lot of time is all this I/O, the input-output operations going on between the memory buffer and the disk. Okay. And then all these partition files are shipped across the network, maybe even, of course, even across racks to other nodes. So there are, let's say, we are assuming here that there are two reducers, okay? So what's going to happen is each reducer, once the task is finished, each reducer will poll the nodes and it will pull its data file. So reducer 1 will go to node 1 and get this file, okay? Reducer 2 will go to node 1 and get this file. And that way they get all the data that are meant for them. Okay, each reducer gets all the data meant for it, collects it, and then does the reduce operation. So, you can clearly see where the problems are. All the time taken to write stuff into the disk and then ship these files across the network are the time-consuming operations. Okay, so now let's go to the Sparc architecture. I can stop and take questions if you want, or I can continue. Just raise your hand or just text me your questions. So you all know that Sparc came out of UC Berkeley, and this is the title of the paper they published describing RDDs, resilient distributed data sets. And look at the figure on the top left, okay? You got nodes. There are, again, 4 nodes, and you got chunks of data distributed across these nodes, okay? So in the first block, you see some piece of data in node 1, the second piece of data in node 2, and the third partition is in node 3, okay? Now, the main difference between MapReduce and Sparc is that in Sparc, we have this abstraction called a RDD, a resilient distributed data set, which is this block. Okay, so the data that are distributed across the different nodes are taken together, and there is an abstraction wrapped around it called RDD. So the user or the developer doesn't have to think about where each piece of information is. Okay, so if you go back to the MapReduce paradigm, okay, here all you have are chunks of data laying around. Okay, there is nothing common linking all of those pieces of data. And that's exactly the major step that these guys took. Okay, they gave us an abstraction that kind of envelopes all these distributed pieces of data across the node, and now you kind of treat that as a singular entity. Okay, it's an RDD, it's a singular entity, and you can apply all kinds of transformations to that RDD, thinking of it as a unitary, a singular object. Okay, so that is the main difference. And conceptually speaking, you have this abstraction called an RDD, and of course, that the main advantage that Sparc gives us is in-memory computation, and we'll look at that a little bit later, and resilience. Okay, so we're also going to look at resilience a little bit later. But just to finish up this these details on the internals. Okay, so you look at the figure to the bottom right. You have all these several partitions of the file. Each partition, each partition is, a map task is applied to each partition, and the outputs are generated. And you can see the outputs are also in a memory buffer, and then you got this sort and spill operation. And in addition to in-memory computation and resilience and all those things, Sparc gives you a lot of, it has optimized a lot of these I/O operations. And, it has sped up the computation, not simply by giving us in-memory computation, but also by optimizing all this in-memory, all these I/O operations. And here is one important way in which Sparc optimizes I/O. Okay, remember in MapReduce you got spillover into the local disk, and it's you're already partitioning it, and you got 500 different tiny little files meant to be shipped to each one of the reducers. Okay, from in Sparc 1.4 they introduced what is known as sort shuffle. Okay, so here each node spills all the data, all the output data into one huge file, a single file, but then it sorts the file by the partition value. Okay, so the output of the hash function, which represents the partition value, is used as an index, and it is sorted by the partition value and by the key values. And now there is only one big file, okay, in each node, and the reducer knows the start point and the end point of its data. Okay, the block of the block in which its data is contained is known to the reducer. The reducer goes to that start point and starts reading from that file. Okay, and this way it pulls, the reducer pulls the data that is meant for it from each node. Okay, so here you have, just instead of having hundreds or even thousands of tiny little files, you have one single file which has already been sorted, and so it is easier for the reducers to go pull their data. Okay, so there are lots. You should know that it is not, whenever people ask you, what are the advantages of Sparc, or what are the main differences of MapReduce and Sparc, and we asked you this question in the quiz, the usual answers are in-memory computation and, resilience and DAG and all that stuff. But there is also a lot of other optimization of the internal operations, and you should be aware of this fact. Okay, so you need to dig into the details a little bit more. Okay, so now you already know that there are transformations and actions on RDDs. Generally, transformations are what are known as lazy evaluation, and actions trigger the actual calculation or computations, right? So now let's look at how lazy evaluation is done in a smart way. Okay, so there are two types. There are actually three levels of data mixing. Okay, one is narrow dependency, the other is wide dependency, and shuffle. Okay, so now each blue box is an RDD, and inside that, those blue squares are the different partitions. Okay, if you are following this figure, each blue square is a partition, and this RDD has 3 partitions. This RDD also has 3 partitions. Okay, so join with co-partitioned inputs, okay, is a narrow dependence. And generally, here you can see the definition of narrow dependence. It simply means that each partition of the parent RDD goes to at most one partition of the child RDD. Okay, so what is happening here is, see, this is node 1. This data is on node 1. Okay, this data is also on node 1. These are 2 different types of data. Okay, let's assume that this is customer details and these are item details. Okay, so they are 2 different pieces of data, but they are on the same node. Okay, and here is an RDD constructed on customer data. This is an RDD constructed on the item details. Okay, now if you are trying to join these data, okay, if all the items that apply to these customers are on the same node, then you only do co-partitioned join. So this the customer detail on this node is joined only with the item details on this node. Okay, you don't have to ship data across nodes. Okay, so this is a narrow dependency, and when you do your co-partition join, again, simple map and filter operations are narrow dependencies. Okay, simple unions are narrow dependencies. When you're doing a union operation, all you have to do is take all the pieces of data and throw them together, and that's what's happening here. You don't need to shuffle them or sort them. Now, when you do group by key, then of course you get wide dependency. So key number 1 could be in this chunk of data, as well as here and here. So now you need to bring those 3 key values to the first block here, to the first partition. So this is a wide dependency because this operation occurs across nodes. Okay, and again, if you have to do a join, such as an outer join, then it will not be a co-partition join. So you will have to take customers from this partition and items from this partition and join them as well, especially if it is a left outer join. Okay, so these are the 2 types of dependencies that we encounter in transformations applied to RDDs. Okay, now let's see how how a complex operation actually happens in Sparc. Okay, how these different dependencies affect a complex operation. Okay, so I made up an example. Let's say Amazon wants to know how many shipments were made to each customer. Okay, and it says something like if the customer is a Prime member, then free shipment is 0. If it's a free shipment, so that is 0. Otherwise, paid shipment is 1. For other members, each shipment should be 1. So you got the member is the key and the value is 1. Here, member is key, value is 1. Member is key, value is 0. Okay. Now A is the RDD on all the non-prime members. Okay. So all you want to do is group the number of shipments by the prime member ID. Okay. So you're doing a group by operation on this RDD, and here you get all the members sorted by member ID and the total number of shipments, okay, in B. So you do A dot group by, and that gives you B, okay. Now C, you need to do one type of mapping, which is, if it is because that is a prime member, the shipment was free, so you are mapping each member ID to a value of 0. Okay, so that is a narrow dependency. You just pick each customer or member ID and you append 0 to it. Okay, so that generates D, and E is as is. Okay, so each customer is already has been mapped to a value of 1. Okay, now you need to do a union of the output of C map and the output of E map. Okay, so that will be D and E, and you do an union. So again, this is a narrow dependency because you don't need to go across nodes. All right. Now, finally, we need to do a reduce operation. Okay. So here you have member IDs and number of shipments. You have member IDs and number of shipments. And here you want a completely reduced set that shows member ID and the total number of shipments. So what is going to happen? So here, each member was directly mapped to the total number of shipments and then passed down here. Okay. So how are the member IDs in this RDD? There is no order to the member IDs. Okay, so they are kind of jumbled up. But here you've already done a group by. So now the member IDs are already sorted. So when you do a join of B and F to get G and to apply a reduce operation here, this is going to be a narrow dependency. Okay, so a join can be either a narrow dependency or a wide dependency. That depends on what is being joined to what. Okay, if it's already been sorted by the keys, if the RDD content has been sorted by the keys, then you're probably going to get a narrow join. Otherwise, you're going to get a wide join. So, does anyone have any questions here? All right, I'll just move on. So here is the more or less complete list of all the narrow dependencies, transformations with narrow dependencies, and these are the transformations with the wide dependencies. And you should always be aware of which one you are applying, because too many of this is going to slow down all your computations. Okay, so yeah, we need to be aware of what type of dependency a particular transformation is going to have. Now, let's go to the resilience part. You already know what that means. So, for example, we have mapped C to D, and then we are doing an union, and all of this has already been done. And finally, we are about to do a join, and this node shown in red suddenly dies. Okay. Now, the metadata here shows that this partition of the RDD comes from this partition, which in turn comes from here. So you go back and construct only that partition, and you are done. Okay. Finally, you can do a join. So I hope this helps clarify visually what we mean by resilient. Okay, that means some of the nodes can die. That doesn't mean, like in MapReduce, you have to start the process all over again. Here we don't. We just do, we just reconstruct the part of the RDD that has been lost. Okay, so now finally, let me try to link all these internals to the actual code that you see. Okay, so when you write this code, this is what should be in your mind. Okay, this is not a very good example, but this is the best figure I could find. So here you have a text file, okay, being read in, and of course the output is going to be a data frame. And you do a flat map, which is you split the line into words. So and then you apply this map, which says which emits word and the length of the word. So all of that is in stage 1. So you can take each line locally, partition it, and make a flat map. And then you can take each word and make key value pairs. Okay. So all of that is here. That is going to be in stage 1. So this is how the DAG is constructed. Okay, you heard about directed acyclic graphs, and that RDDs optimize their operations using DAGs. Okay, so now when you do a group by and then a map of this nature, okay, so you have a key and then value, and then you're calculating an average. So this has to go across lots of key values. So when you do operations of that nature, there is going to be a shuffle or white dependency, okay? And then the rest of the stuff is again, it's gonna happen with narrow dependencies. So the DAG has 2 stages: stage 1 with all narrow dependencies, stage 2 with all narrow dependencies, and in between the 2 stages, you have white dependencies or shuffle. So when you're writing, and I'll show you another piece of code later on, when you come to this point, you can either persist this or cache this, and then you'll be able to reuse it. And I'll show you a very good example of where this comes in handy. Okay, so that's about RDDs, and then I think some of you have already started reading up on data frames, and it is I shouldn't say extension. It is an improvement on the RDD framework. Again, you know the differences between RDDs and data frames. When you're asked in an interview, you'll probably say that the data frame reads in data and infers a schema, and so a data frame has has a relational schema associated with it, and RDDs don't. Okay, that is the standard answer, but you really need to dig in and know a little bit more about what a data frame is. Why do we need data frames? Why can't we just use RDDs? Okay, so the main again, this is another level of abstraction. Okay, remember when we went from MapReduce to RDDs, an RDD itself is an abstraction on top of the partitions that are spread across the entire cluster. Okay. Now the data frame is another level of abstraction. It is a distributed collection of rows that are organized into columns. Okay. So it's essentially a table, just like a table you would see in a relational database. And the main advantage of that is you can connect to any RDBMS, in unstructured stores, okay, and pull data into a data frame. So there are, you can read data from databases directly into a data frame. Okay, so that is the data processing advantage that data frames give. And again, because it is very similar to, it has a relational schema and it's similar to RDBMS. You can have a logical plan. You can optimize the logical plan. Whenever you do a query, you can generate a logical plan, optimize the logical plan, and then generate a physical plan. And all of that adds a lot of optimization and speed. Okay, so you are able to repeatedly query the data in the data frames and do transformations in an optimized way. Okay, so those are all the advantages of data frames. So I think that covers all the major, major pieces of information you need to know, the background that you need to move on to machine learning, especially ML with Sparc. Okay. So again, are there any questions? So very quickly, there are 5 different features, important features of ML. Okay, one is the data frame, and that's what I've been leading up to so far. The next is a transformer. Now, if you think about machine learning or modeling, okay, there are 2 main things we do. One is we take the raw data and we do all kinds of transformations on the raw data. Okay, you need to clean the data. You need to deal with missing data. Okay, you need to verify the data, which is data integrity. You need to know if the sources are reliable and all that stuff. So you end up spending a lot of time just working with the raw data and putting it in a format that will be compatible for training the model. Okay, so the input to the model is never the raw data that is in the data frame. Okay, so you need to build lots of transformers, and you apply these transformers to the data frame, and the output of the transformers will function as the input to the model. Okay, and the estimator essentially takes this transformed data and estimates the model parameters. Okay, and a pipeline is another level of abstraction that Sparc ML gives you. It allows you to construct all these transformations and the estimation as a sequence, okay, and then just apply the data frame at one end and you get the results at the other end, okay. So let's see how this works. So this is an example of training a model. You set up a pipeline. This is going to be the estimator. You tokenize, you do transformations, and then you apply the model. Okay, you do logistic regression. When you say fit, it actually fits the model to the data, and you get the output of this process is a logistic regression model. And the testing part, you again set up a new pipeline. You start with the tokenizer transformations, and you apply the data to the model, and you calculate the output. Okay, so this is what we mean by pipelines. Okay, you construct a pipeline for training and pipeline model for testing, and you can see this in the example notebooks that Elena has put up on assignment 4. So in MLlib, you have lots of algorithms already available for classification or supervised learning. You have logistic regression, support vector machines, and naive-Bayes, and clustering. This is a fairly old list, but you got a lot. I think in the latest version of Sparc ML, you have lots and lots of algorithms available and lots of variations available. You have decision trees. I don't think I have listed them here. You also have decision trees, and there are methods to hyper-tune all the hyperparameters of the decision trees. So, for example, you can train one decision tree and then do a boosting. So you get a sequence of decision trees, and you need to optimize the parameters of how those decision trees are all combined to generate a single decision. There is a framework for doing that kind of hyperparameter optimization automatically. Okay, so there's just a tremendous amount of power in Sparc MLlib. So I encourage you to explore a lot of these functions. It's going to be very useful. So finally, an example. Okay, so this is how I think this brings together all the concepts we have discussed so far. Okay, you know from your machine learning courses that gradient descent is, probably one of the more computationally intensive machine learning algorithms. So here W is the network of the weights in the neural network, and in each iteration, you compute the gradients and you adjust the weights. Okay, and this is the learning. Alpha is the learning parameter. Okay, and if you have ever coded this in, I don't know, Fortran or C, you know how many iterations, how many calculations each iteration takes. Okay, so here is the sample implementation in Sparc MLlib. Okay, you basically read the data, and you have a parsing function as usual. As I said, this is what cleans up the data and transforms the data and all that stuff, and you cache the data frame as a value, and now you create the vector of weights. And here is the interesting part. Okay, so here you are iterating several times, but each time all you do is you grab this data frame or RDD and you apply this map, which basically takes each input point and calculates the gradient, okay, the gradient value, and then you reduce it. So you just add up all the gradient values and you adjust the weight. Okay, the next time you come back here, again you grab the same point and you do the same operation with the new updated weight. Okay, and remember that this is in memory. Okay, so that is where, so you're maintaining this in memory and you are doing several iterations of this operation till you reach an asymptote of the error. Okay, so this clearly illustrates why we need all this, all these frameworks, and it illustrates how Sparc really speeds up things. Okay, so any questions? I thought we will do a code walkthrough, but I think Elena wants to address other issues also.
Let's talk a little before the code walkthrough. I think everyone is free to ask question in the chat, or if you want to speak, just have to unmute yourself. I don't see any question by now. And this is the part which is, let's say, the technical part, which if you look to the classroom, there are a lot of reading. Just Professor Gopati took the work to summarize a lot of reading we have for the last, let's say, 5 weeks in this lecture, so you grasp the picture. This is a summary of all the reading which are in the classroom. So why he was the decision to do that? For instance, many of you are tempted to jump directly to what is step-by-step instruction of the assignment, of the walkthrough, and miss the big picture of what we are doing. It's just, and this is not helpful, because at the end of the day, what you understood in this class has to do that you can connect what you are doing in this step-by-step instruction with this thing we have here summarized, which is, let's say, the theory behind all this technology we are using. And it's very important that you ask yourself, otherwise everything defeats the purpose. Like in the beginning of the course was stress. The course of big data analytics, we are not going to teach you new algorithm of machine learning. They are the same algorithm which you already were exposed in the previous courses. What we are studying in this course is how new methodology which is based on the new technology to deal with big data. And this is the thing you are getting from this class. So, and of course, this new technology has behind the scene all this, let's say, very advanced setup like is MapReduce, and then the paradigm of in-memory analytic, which is the Berkeley University, the Sparc engine design. So you have to keep this in mind, and keep in mind also all these things are changing constantly. There is no such a thing in big data technology that what you train it today as a technology, as a version of, let's say, a version of the software is going to be the same next in 6 months. Everything as a version of of software change. So that's why it's so important you understand to connect what you are doing as a step-by-step instruction to the thing which are in reading, and that is the main purpose of this lecture. So other thing I want to stress is, keep in mind we have to go step forward of this. What is the step forward? How is this implemented in the cloud? Because the idea of MapReduce and having thousand of commodity computer and everything in the disk, you understand this implementation in the cloud is something more challenging. And for Sparc, we have what is the concept of object storage. So you have to think about all these concepts and read a little more about how is this implemented in the cloud. So every time you do something and something happens, you understand that there is no magic, because it's very nice to see in the classroom, sometime in the Q&A part, oh, the magic did it. There is no magic. And the most important is that you try to understand what is happening. Moreover, when we work in the cloud, many of the resources you are using, these are not dedicated to your resources. We are using shared resources most of the time. This is, for instance, the case with object storage. So you don't know where is your data. As soon as you upload this to the object storage, this is managed in the way the resources in the cloud work. So there is no magic that sometime it happened in 30 seconds, sometime it happened in more than 3 minutes. And it has nothing to do with the, let's say, the level of the technology we are using. This is just this concept of object storage. Moreover, in addition to this, from time to time, some services have, let's say, have outages, like this is normal thing in the today technology. So one important thing I want that that you are aware, that you go to Bluemix and you check if there is reported issue with the service you are doing. Not just for the assignment. For the assignment, we find out and we post announcement. But this is just part of the practice. You have to learn how to work in the cloud. It doesn't matter if it's AWS, Bluemix, or Azure. It's mostly the same thing. It's just the interface is slightly different, but the concept, everything is the same. So my suggestion is you try to digest. We are already almost at the end of the course. Time is just running very fast, and try to digest as much as possible and to ask questions. So the most important is why. Sometimes the question is not, oh, this script is not working, and if the TA is helping you to make it work, it, done. I don't think there is nothing useful of this. Yeah, you are going to finish the assignment, but what useful you get of this? You have to understand why is this working, and the most important question in graduate school and in any of the courses is why. So that are my main suggestion. I have some other stuff, but we are going later. So let's see. I see some question. Gopati, do you see question in the chat?
No, I don't. I haven't seen
Okay,
anything.
there is one private to me which says,
Okay.
can we run the ensemble model in MLlib in the Spark? If they can run the ensemble model, that is the question. The problem is the question goes privately to me, so that's why you don't see it.
Okay.
So to everyone, please direct your question to everyone because I cannot keep up with everything. Go ahead.
Yeah. Did you say ensemble model?
Mm-hmm.
Okay. Yeah, definitely. You can actually here, this reduce is working across all the points, but yeah, it's definitely possible. You can do, you can code it yourself, but I'm not sure if there are any specific API functions available for that. But yeah, it's possible, definitely.
Let me add, it's possible, but it needs research and time dedication. My suggestion is first do the assignment, and if there is time left, start exploring. And there is a lot of reading because everything you are going to use, you understand that there is documentation for everything. And in order to answer the question why and how I'm using, it has to be researched. And this is not just this thing. Google search about something is not going to work. The most important is you understand the key of the thing we are doing, and this is my main suggestion. Okay. You had something else. Go ahead. Gopati.
Yeah, the should I do a code walkthrough of the Titanic assignment? Do you think that will be useful?
I think they have a very detailed walkthrough, but if there are a question, if you think this is going to be helpful, go ahead. I don't know. I don't see what people are saying. I don't see any feedback regarding this.
Okay. So let's see.
So since there are no question, go ahead and do it.
Okay. So hopefully this will help you get through the actual assignment, which is to do a logistic regression on the low birth weight data. So let's just make sure you understand the different operations going on here. So this is just importing all the packages. I'll try to run the cell as I go on. So here we just defined a parsing function. As I said, that's going to be easily 60% of your modeling effort. Okay, the first part is to pull the raw data, clean up the data. You need to trim things. You need to transform between different data types and things like that. And it always takes much longer than you would expect, and you generally think that that's going to be the easy part, but it is not. So the parse function here is actually a very good example of the type of operations you will do. So for example, here it takes each line, splits it up, and then looks at the fifth column, and if the value is 1, so if it is strictly greater than 0, it gives it a label, say survived is 1, else it is 0. So you are basically renaming something here. And then you are combining some of the, in this line, you are combining some of the values in a specific order. So you are taking, I believe, the class. This one says it was the first class or second class passenger. This is the age, and this is the gender. Okay, so you are combining all of them into a string. These are typical operations that you will do to transform your raw data into something suitable for machine learning. Okay, and then finally it is returning the text value with a prefix and a suffix. Here the prefix is the ID, the member ID or passenger ID, and then it sticks in all these transformed values in between. So this one has number 1, the class the passenger was in, 2, the age, and 3, the gender, and then you attach the label as survived or not. Okay, so this is just a function, a parsing function, and here are the top 5 rows of the data. Let's see, yeah, top 5 rows. The first row has is the header, so it says name, passenger class, age, sex, survived, person ID. This is how the raw data is, and then you apply the parsing function, and it changes the data into this format, which is probably the format that is more suitable for training. You know, this is just an example. So, and then the one thing that it does that really makes sense is it brings in the member ID to the front. Okay, it was at the end of the raw file. It was the last column in the raw file. Now it is the first column in this file. Okay, and again at the end is the training label. Okay, so this is nicely reordered data. And then here you are splitting the data into training and test sets, 80%, 20% as usual. So there it is. Here the filter, you know, is removing the header. So now you have only the prepared data. And yeah, so and here is where you are setting up the pipeline. Okay, so the pipeline here has 3 stages. The first stage is the tokenizer, okay, which takes person info, which is a long string, as you know, from here. So it says first the passenger class, age, and gender, and this string is given to the tokenizer. The output is words. Okay, the column is called words, and the output of the tokenizer is applied here, and then you are collecting the features. Okay, so this is basically the feature engineering, you know, very simple example of feature engineering. In fact, there is really no feature engineering going on, but in, you know, in a real world example, you will do things like, you know, normalize the data. You calculate the mean, subtract out the mean, divide by the standard deviation, that kind of stuff. So you are preparing or converting a string of numbers, a series of numbers into percentages and things like that. So that is feature engineering. So you get, at the end, you get the features which is fed into this model. Okay, that's the logistic regression model. So let's prepare the pipeline. Okay, I think I did that. And then, yeah, don't worry about the comment here about some deprecated function build. So here, finally, the model is being built. Okay, and this shows the model parameters. All this comment is saying is it says you should change the weights to coefficients. So you can play around with that. And then here is the training data. And now you are actually applying the test data to the model, and you have the predictions. So you got, you know, a 21-year-old female in the first passenger class. The prediction is that the person will survive, and it gives you a confidence interval for the probability. Okay. And now you are actually calculating measuring the performance of the model. You got the F1 measure accuracy, test error, precision, and recall. Actually, this is the, I believe this is on the training set. Okay, so this is the performance on the training set. So how well did the model actually capture all the variations in the data? Okay, the variability in the data. So precision is 82%, which means 82% of all the people predicted to survive actually survived. Okay, and this is the recall, which is also called sensitivity. So you can go through these measures and see how they are calculated. And here you're calculating the performance of the model on the test set. So you can see it is slightly, the recall is much lower. Here it was 76%. Here on the test set it is 61%. Precision was 82% on the training set, and it is 80% on the test set. That is to be expected. And here you have the confusion matrix, which shows how the predicted categories and the actual categories split up. Okay. And the area under the ROC curve and the PR curve so are pretty good. So it is about 74%. The area under the ROC curve is 74%. So this is actually a very nice template for you to take and play with other data sets, and you're going to be doing the same thing for with the low birth weight data. So do you have any questions? Yes, there was a comment from Rick. He said that this is Python, and I was showing the prior code in Scala. Yep, that's true. Usually, okay. Usually when you look at the documentations, you will have sample codes for both. The Sparc API document has sample code for Scala, Python, and I think Java in some old versions, but not in the newer versions. So you can go back and forth between the different languages. It's better to be language agnostic. You never know what your employer's environment is like. There are some people who use Scala, others use Python. And there is the question about gradient descent. Rick, I didn't get the question. And Sarah says there was a partitions error when doing part 2. Okay, I need to know more details on this. Which cell exactly caused the partition error? Okay. So, Rick, what is your question about gradient descent? Okay, so when does the gradient descent know? When it reached the optimized value without passing over it. Usually, okay, there's like 2 or 3 different ways of doing it. Okay, one is with a cross-validation data set. So you take your training set and you hold off some data from the training set, Okay, this is in addition to the test set. And every time you train the model, you check against you calculate the error over the validation set. If the error keeps going down, you continue to train. Okay, so you are going to measure the rate at which the error is decreasing. Okay, let's say in the first step the error went down by 10%. The next step it went down by 8%. Okay, so you have to fix a threshold that says if the error starts decreasing by less than 0.1%, I want to terminate training. Okay, that's one way to do it. So that would ensure that the model will have good generalization, because you are not actually training on the cross-validation set. Okay, you are only using it to measure generalization. The other way is to simply look at the global error and see how much, again, how fast the global error is decreasing. So by global error, we mean the mean squared error between the actual output values and the desired output values. Okay, if the mean squared error decreases by less than a certain percentage, then you terminate the training. Okay, and there are, of course, more sophisticated ways of doing it. But this is by far the two most popular ways of terminating training. The other question is how to create graph in Sparc. Okay, so similar to MLlib, you have GraphX, which gives you lots of very easy to use functions. And the GraphX API is again available both in Scala and Python. And you can just play around with it. It's a good. Do you mean a plot? Just a plot? Okay, I'm sorry. I think Val means how do you plot data? There are examples of There are examples of two plots in the tutorial. Yes. Actually, we found an issue when the notebook generates a plot and you save it as an HTML file and then load it up for review. Somehow the graphs don't show up. So it'll be good for you to make sure that after you load up your HTML version of the notebook, you can still see the plots and graphs. Yeah, the sum squared error. Yes, Rick asks if the termination criterion is the lowest sum squared error. Yeah, I mean you don't have an absolute value on the sum squared error. You don't know what it is, and it's kind of meaningless. So what you do is look at how fast the sum squared error is decreasing from step to step. Okay, so if it is decreasing at a reasonable rate, then you can continue to train. But if it is decreasing at a very, very small rate, low rate, then it's going to take tens of thousands of iterations to get a significant change in the weight values. So that's what you use. You look at the rate at which the value error goes down. Yes, partial derivative. Yes, that is correct. So are there any other questions?
I don't see more questions. Oh, here. Yeah. Any of these specific questions, you do a little research, just Elena posted in the chat a link to follow the sample notebook.
Yeah. Oh, yeah. That one is about the pixel dot. It's a nice visualization.
Yeah, I got it.
Yep.
So, in meantime, until you think maybe you will have more question, I just want to stress again that you understand that what we are using is the top technology today in the cloud, which is as a service. What that means? As a service, that means you don't know what are the dedicated. They are not dedicated to you specific resources. What you are using is a service. So every time you get this different response time, don't think that there is a book in the system. This is not about book. This is about the way the resources are balanced at the time you are using this intense computational tool. That is one of the things. And the other thing is I want to share a screen here um, for a minute about, let's say, do you see my blooming screen?
Yes.
Yes? Okay. So in meantime, every time you feel you frustrated, you don't know what is happening, the first thing again is think about you are using service. This is not dedicated to your resources. This is a service. Secondly, and you use them very seamlessly with a browser, and sometimes the issue is the browser. Why sometimes the issue is the browser? Because the only way to get to these services is through the browser. So that's no magic, no books, nothing like this. So if you have any doubt, click to support here, go to status, and you will find out what is the current status. Is there are problem, whatever problem right now they are in three services. None of these three services we are using. And if you want to go back to check something which happened, you can see all the services are in green. And when something happened, it appeared to the right hand, and you can see that in November 17 at 1 p.m. it was reported issue in data science experience. Maybe you were working exactly at that same point. And also you can see that at some point the object storage, I think I'm going uh, very fast. Okay, here is the object storage. And if you remember doing some work for class in September 13, which was Monday, it was on November 17, issue with the object storage. Issue with the object storage in November 17, which was reported and of course was fixed. You see all this green. So this is one of the things I'm showing you. So in your future work, you know how clouds work. You use the service. You make sure, very important, we understand this is very intense course and we are running out only almost out of time, but make sure when you run some service, you go and you view the documentation. Without documentation, even though you have step-by-step instruction, you have to get better picture of what you are doing and what are the resources you are doing. And I can tell you, when you get a costume to this, you just are starting. You will have time after this semester is over to explore this on your own with more time. Just keep in mind, try to read as much as possible and to answer the question, why is this happening? So that is the thing I have by now. Take advantage that we are exposed to the what is cutting edge technology in this field, and that is what you are going to use at work. I see Gopati is not sharing anymore. Oh, because I got the ball. Oh, okay. I see. Um, I'm returning to his presentation if any of you have any question. And in meantime, Patrick, do you have any comments? Patrick?
No, no.
No,
Everything
no.
was covered. Nothing.
Okay, great.
Yes, great presentation.
I don't see more question in the chat. So we have just 2 weeks until the end of the semester. But again, you will have time to digest this and to understand that whatever we are doing, this is the approach to deal with big data. And all this technology, which is the top today, all the version of software are changing constantly. You are just trained here how to deal with this cutting edge technology to deal with problem in mostly machine learning and text analytics for what is important for big data. You can unmute yourself if you wish to speak. Okay, I don't see any more questions. So I wish you first good luck with this last assignment in the class. I know you feel at this point overwhelmed, but time will pass and you will feel much better when you got the time to reflect and to digest what we are doing. And of course, to have a wonderful Thanksgiving.
Thank you. Thank you.
Good evening.
Thank you.